Hello and welcome to lecture 9 on NPTEL online certification course for aerodynamic design of axial flow compressors and fans. In last lecture we were discussing about maximizing the per stage pressure ratio. That's what is a recent trend. This is what is a requirement from industries. Especially these requirements are for aero engines where our size, our weight and our operability, that's what is of major concern. It says in order to increase your per stage pressure ratio, we need to increase our peripheral speed of the rotor. We need to increase our axial velocity, that's what is going inside my engine. We need to increase the blade deflection of rotor in order to achieve high pressure rise. And for first two cases we have observed, like with increase of peripheral speed or by increasing your axial speed or axial velocity, that's what is lead to have shock formation will be happening near the tip region. Okay, and that will lead to increase your losses and blockage to your flow, that will be reducing your efficiency. Using your higher blade angle or higher blade deflection angle, that's what will lead to flow separation. Since we are working under adverse pressure gradient, we will be having the separation of flow that will be happening on my suction surface of the blade or maybe on the pressure surface of the blade. Now when we are having higher deflection angle for the rotor, and if we are looking for axial exit, my design for stator also will be very challenging. So that's the reason why people, they are finding different ways to address these issues. So as we move ahead, we will be discussing what all development activities which are going on globally to address these issues. Now let's move with the next case. Say we are putting a term, that's what is say our axial momentum. So we have three major velocity component, rather fourth velocity component we are correlating with our diffusion process. Suppose if I consider I am having my axial velocity, so my axial momentum equation, that's what will be written by m dot into Ca2 minus Ca1. Okay, so this is what is nothing but that's what is representing my axial force component, and this axial flow component, that's what will be taken care by using your thrust bearing. Okay, so this is what is responsible for your mechanical and aerodynamic damage to the rotors. Okay, so if we look at here, say for this case, we know we need to provide certain amount of clearance between casing and rotor in order to have the free rotation of my rotor. We realize this is what is a mechanism where I will be having say loss, that's what is happening, that's what is called tip leakage loss. So if I will be putting my gap between this rotor and casing to be say certain amount, it will give better pressure rise and better efficiency because I am able to reduce my losses. Now what happened, because of some reason, suppose if I consider your axial force, that's what is acting in axial direction. So you can see this is what is say my axial direction. There may be possibility that my rotor will try to move in forward direction like this. It will be moving in upstream direction. So what will happen, what clearance we have provided between casing and the rotor, that's what is going to reduce. And there may be chances that my rotor will be touching to my casing, and that's what will be giving you catastrophic failure. So in past many such failures they are happened. Okay. Now if I will be going in other way, suppose if I consider say my axial force, that's what is acting in say downstream direction. So if this is what is your case, you can see I will be having the gap between rotor and casing, that's what is going to increase. If this is what is your case, you will be having the tip leakage flow contribution to be increased, and that's what will be lead to reduce in pressurizing capacity of the rotor, as well as it will be reducing your efficiency. Okay, so we need to take care of what we say, that is nothing but the change in our axial velocity, because that's what is responsible for your axial momentum. Now next we are having more component, that's what is my radial component. So this is what is representing my radial direction. So what it says, my radial momentum, that's what is given by m dot cr2 minus cr1. Okay, this radial force, that's what has nothing to do with your steady state aerodynamics of the compressor, and mainly my journal kind of bearing, that's what will be taking care of this situation. But depending on the lubricant flow and its property, the force can aggregate the cyclic shaft motion, that's what is known as whirl. Okay, so what will happen, my rotor or my shaft, that will be rotating off center. If this is what is your case, you will be having catastrophic failure of your rotor. So there are mechanical failures which are happening because of change of this velocity components. So we are not discussing anything in sense of mechanical aspect, but change of your velocity components, that's what will be bringing you the change in your structure. So change in your flow mechanism, change in your operation. Okay, one more component what we have discussed, that's what is our tangential velocity component. So that's what is responsible for my tangential momentum. So my tangential momentum, I can say that's what is written by m dot into cw2 minus cw1. What I know, this tangential velocity component, that's what is responsible for generation of my torque. So that's what I am writing here in sense of my force into distance. That's what will give me a power as an equation. So you can say my specific power, that's what we have already discussed, u2 cw2 minus u1 cw1. And if I will be correlating using my cosine relation, we have derived with my work done equation to be 1/2 say c2 square minus c1 square plus 1/2 v1 square minus v2 square. This is what all we have discussed. So now you can understand we are having mainly three momentums, that's what is happening because of your change of component of velocity. Okay, and we need to be very careful in sense of doing design. We need to take care of doing our mechanical design as well as when we are doing our aerodynamic design. Okay, now this is what will give you overall idea in sense of what all will be the use of our velocity components. Now let's move towards the next. So we are more interested in different kind of configuration, stage configuration, what we say. That's what is applicable to your fans as well as compressor. What all are the different configuration? It says we can go with only rotor configuration. We can use stage with inlet guide vanes. We can use stage with outlet guide vanes. We will be having combination of inlet guide vanes, rotor and outlet guide vane, and we also can have contra-rotating kind of configuration in which my rotors will be rotating in opposite direction. So let's try to understand what all are the application of such arrangements. Okay, so we are discussing at this moment for design of say axial flow compressors and fans which have different applications. Okay, so let's try to understand what all will be the use of these fundamentals for your application. Now let me move towards say next slide. Say this is what is I am having stage without guide vanes. I say I am having only rotor. So here if you look at, this is what is representing my rotor. Okay. Now there are many applications where you have found there are only rotors. Suppose if I consider the cooling fan, if I look at say my exhaust fan, okay, my cooling tower fan, my wind tunnel fan, if you look at, they are having this kind of configuration in which we are having only rotor. Even for high bypass ratio engine also we are having big size fan. Okay, but realize one thing, fans what we are defining, that has a different definition for aero engine, that has different definition for our application part. Okay, now here if I consider this is what is say my station 1 and 2, it is at the entry and exit, I can put my section with this aerofoil, and if I will be drawing my velocity triangle, let me consider for this fan my flow is entering axially. So, I say my absolute velocity, my axial velocity, that is what is same. I know this is what is my peripheral speed at the midsection, and this is what all we have discussed is representing my relative velocity component and my blade angle at the entry or airflow angle at the entry. Now, my flow that will be coming out with relative velocity V2, okay, and I will be having my peripheral speed, and if I will be connecting, that is what is representing my absolute velocity component. Now, we assume our axial velocity is same upstream and downstream of my rotor. So, that is the reason my CA I am assuming to be constant. Now, this is what is my beta 2, that is what is my blade angle at the exit. This is alpha 2, that is what is my absolute flow angle, and you can see I am having my whirl component, that is what is CW2. Now, here we are representing our static pressure rise. When I say static pressure rise in my rotor, as we have discussed, my relative velocity component, that is what is responsible for generation of my pressure rise. So, that is what we are writing as half rho V1 square minus V2 square. Now, this V1 I can represent from this velocity triangle using my Pythagoras. I can write down CA square plus U square minus this V2 we can represent in sense of this equation. Now, if once I will be simplifying this equation, that is what it says, my static pressure rise in rotor, that is what is given by this equation. So, let me put this, say static pressure rise, that is what is say rho u CW2 minus half rho CW2 square, and my specific power or the power required for running of this fan, that is what is given by u into CW2. Now, if you look at carefully my static pressure rise, what I am expecting, this is what is coming a negative term. What you mean by this? It says my static pressure rise, that is what will be decreasing because of increase of my CW2 or because of presence of my whirl component at the exit of my rotor. Okay. So, this is what is a component, that is what is responsible for my static pressure rise to be lower. But at the same time my specific power, so you can understand my specific power requirement, since my pressure rise requirement, that is what is say lower, my power requirement also will be going lower. So, there are many industrial applications where additional pressure rise may not be required. Okay, you are not looking for pressure rise. Okay, and it says it may increase the cost of your fan. Now, just look at, suppose say you are having your exhaust fan. That exhaust fan, it is made up of only rotor. Okay. Now, when I say it is made up of only rotor, there is a meaning, there is a reason, or the whole purpose is only to supply the mass flow rate, to supply the air. My pressure rise is not coming into the picture. It may be having pressure rise, but it is lower. Suppose if I consider the application say for wind tunnel. So, for wind tunnel, the whole purpose of providing the fan, it is let my flow to flow through the this section. Okay, and fan will be overriding what all friction losses, that is what is happening in our wind tunnel. Okay, so you can say my velocity requirement, that is what is say higher, or my mass flow requirement, it is higher, and it need to address the pressure drop, that is what is happening within the circuit. Same if you are looking at say for cooling tower, you will be having pressure rise of few pascals. Okay, so there we are only having this rotor kind of configuration. These days people, they are working on say other configuration, that's what is called variable pitch fan. So this variable pitch fan, it is not a new concept. People, they already have explored. So many times in order to change the flow through wind tunnel, we used to change the angle of our blade such that we can increase or decrease the speed through the test section. Okay. So many times people, they are using mechanical devices in order to use variable pitch kind of configuration. So basically variable pitch in the sense we are managing our CW2. Realize that thing. Okay. When I am changing my angle, say for this blade, if I am changing my angle, it says basically I am managing my CW2. Okay. Now let's move. Suppose if I consider I am looking for reducing, or say I don't want my whirl component to be coming out from my rotor. So that's what it says, my CW3, that's what is equal to 0. In order to achieve that, what we need to do, we will be putting one stator or inlet guide vane here. Okay. So this inlet guide vane, if I am looking at, I will be having my flow, that's what will be entering inside my rotor at some angle alpha 2 with some absolute velocity C2. I know what is my peripheral speed, I will be getting what is my relative velocity component. Okay. So this is what is my beta 2, the angle at which my flow is entering inside the rotor. When it is coming out, okay, it will be having say my relative velocity component V3, I will be having my U component, and just look at my exit will be axial one. That means my C3 and CA, they both are equal. Now what is happening? You know what we were discussing about the whirl component, that's what was coming out from the rotor when I am using only rotor, that's what is we have addressed by incorporating this inlet guide vane. And here if you look at, I am having my whirl component, this whirl component, that's nothing but, you know, if I will be writing my equation for my static pressure rise, it says this is what is getting added up. It is 1/2 rho CW2 square. Now the reason is this is what is a negative swirl we are providing by incorporating inlet guide vane. Okay. So this is also one kind of configuration, that's what is possible, in which my rotor that will be having say upstream inlet guide vane. If this is what is your case, your specific work or specific power requirement, that's what will be given by U2 into CW2. Okay. Now we will be discussing in detail about the inlet guide vane application for the engines. Let me tell you, there are many applications. Suppose say we are discussing about the mining fans. Now in mining fans, they would like to exit the flow in axial direction, because this flow, that's what will be connected with your ducts. So under that configuration, we are having this inlet guide vane that will be followed by the rotor. Okay. Many times in order to modulate the mass flow rate entering inside the rotor, that also is done by using these inlet guide vanes. Okay. Rather you can understand, say if I am using say variable pitch configuration for the rotor, maybe during a rotation condition it will be little tricky and challenging in sense of mechanical design. Okay. So when we say it is a mechanical design, then in a rotating configuration, change of this pitch, it is very challenging. So that can be modulated by using this inlet guide vane. That's what will be having say, you have modulation for your mass flow rate. Okay. So basically what whirl component we were getting at the exit, that's what we have managed by incorporating the inlet guide vane. Now you will say, sir, why don't we try by providing the exit or say outlet guide vane. So this is what is a configuration in which we are having outlet guide vane. So let me take at say mid section, we are having different stations, and for destinations, if I will be writing, I will be having this kind of velocity triangle. Here in this case, what we are finding, here also we are having our exit to be axial one. So, you can see this is what is my axial exit. Okay. So, by providing this outlet guide vane, basically we are taking care of our wall component that is coming out from the rotor. Okay. So, if I will be writing my pressure rise, that is what will be coming to be slightly lower compared to our earlier configuration. Okay. And my specific power, that is what will be the function of U into CW3. Okay. So, what is my requirement? Accordingly, I need to design the configuration. Okay. Now, with this, you will say, sir, why don't we try with inlet guide vane and outlet guide vane both, and I will be having my rotor in between. So, it is like a multi-stage configuration kind of situation. People, they used to say this as a 1/2 stage compressor. Okay. If this is what is your case, you can say my flow that will be entering with some absolute velocity, okay, with some angle alpha 2. I will be having my peripheral speed. If I will be putting, this is what is my relative velocity component, I will be having my blade angle. Same way, if I will be looking here, this is what it says my wall component I am imparting by using inlet guide vane. So, at the entry of rotor, we are imparting our wall component. Now, this is what it says negative wall component, because that is what we have realized if we are using inlet guide vane. Careful, based on what kind of inlet guide vane you are putting, your wall component will come. Here, for this kind of configuration, it is coming negative wall. It may be possible that you will be having your inlet guide vane that will give flow with positive wall also. Okay. So, do not get confused with this part. Now, in sense of exit, this is what we have realized. We will be having my exit wall component, that is what is say my CW3. Now, what we want to do, we are looking for our axial exit. So, if we are looking for axial exit, we will be having stator vane that will be placed here. Okay. Now, when we are doing this kind of design, we are assuming say symmetrical kind of configuration, and it says my CW2 and CW3 to be same. What it says my alpha 2 and alpha 3, that is what we are assuming to be same. If this is what is your case, you will find, you know, like my static pressure rise for the rotor, that is what will be double. Okay. At the same time, my specific power requirement, that also will be double. Okay. So, kind of application what you are looking for, accordingly you need to decide with the different configuration for your rotor and stator. Okay. So, we have seen we are having say only rotor kind of configuration, we are having rotor that will be, you know, having inlet guide vane. So, stage we can say inlet guide vane and rotor. We also can have rotor and stator configuration. We can have inlet guide vane, rotor and stator configuration. Now, let us discuss with some other approach. Okay. Here if you look at, this is what is representing the contra-rotating configuration. So, this rotor, suppose say first rotor, that is what is rotating in say your clockwise direction, then my rotor 2 that will be rotating in opposite direction, it will be rotating in counterclockwise direction. Okay. So, this is what is very interesting case when we are discussing about different configurations. So, here if you look at say this is what we can say as inlet guide vane and outlet guide vane, there are many configurations in which we are not having say inlet guide vane and outlet guide vane in combination with contra-rotating fan. This kind of struts, that is what is provided only for the support. But let us see, suppose if I consider I am looking for my flow to enter at certain angle. Okay. So, this is what is my angle with which flow is entering, say it is my C2. This is what is my peripheral speed of rotor 1, and if I will be connecting, that is what is representing my relative velocity component. So, this is what is known to you. Now, you are fundamentally clear how your velocity triangle at the entry that will be happening. In line to that, if you are looking at, we will be having exit with relative velocity v 3.1. Purposefully I am writing here 3.1. This is what is my peripheral speed. I will be having my absolute velocity c3, and these are my angles. Relative flow angle, we are having absolute flow angle, and my axial velocity, that's what is coming to be same. Now this is what is my exit velocity triangle from rotor 1. Now what we know, say this rotor, that's what is rotating in one direction. I am having my second rotor, that's what is rotating in opposite direction. So what happens? Let's see. Suppose here I am making assumption, say my velocity, my absolute velocity, that's what is coming out from my rotor, that's what will be entering at the same angle to my rotor 2. Okay. So if I am putting my peripheral speed here, you can see this is what is making a kind of velocity triangle like this. And if you look at my relative velocity at the entry of my rotor 2, that's what is coming to be v 3.2. You can see that's what is larger compared to your entry condition for rotor 1 and exit condition of rotor 1. Okay, and this is what is because of what whirl component, that's what is coming out from my rotor, that will be getting added up. You just try to understand here, this is what is representing my positive sign, and this is what is representing my whirl component in opposite direction. So what basically is happening, just look at, if I am writing my specific power of rotor 1, it says u Cw2 minus Cw1, and here if I am writing for my rotor 2, that's what is given by u Cw4, that's what is nothing but my exit configuration here, minus Cw3. Okay. So here you can see you will be having your specific power for rotor 2 to becoming large. Okay. And if we are talking about the static pressure rise for both the rotors, that's what is given in sense of my relative velocity component. For rotor 1 it is V2 and V 3.1. For rotor 2 that's what is V 3.2 and V 4. So by incorporating this contra-rotating configuration, we are able to achieve high pressure rise. Now let me tell you, there are many advantages of this contra-rotating configuration. Okay, you can understand, suppose if I am removing my inlet guide vane and outlet guide vane, it says there is no need of stator in between two rotors. So if I am eliminating my stator between two rotors, that's what will be reducing the length of my engine. Okay. It will be reducing the weight of my engine. If I am talking about application for say engines, that is application for aero engines. Okay. So what it will be doing? It is reducing the length of my engine, it is reducing the weight of my engine, that's what is improving the fuel economy. Now let me tell you, say for recent fighter, that's what is 5th generation aircraft F-35, they are having engine that's F-135 made by Pratt & Whitney, in which all the compressor stages what they have designed, they all are of contra-rotating configuration. So the concept of contra-rotating is, it is applicable for your compressor, it is applicable for your fan, it is applicable for your turbines, it is applicable for your propellers, it is applicable for your turbine. And whole fundamental for all this application, it is to deal with this whirl component. Okay. So what is happening? My whirl component, that's what is coming out from my rotor, we are not managing for all current configuration. Let it be rotor, say inlet guide vane and rotor configuration, say rotor and say stator configuration, inlet guide vane, rotor and outlet guide vane configuration. For all this, we are basically trying to do something in sense of avoiding this CW2 or whirl component coming from the rotor. And for contra-rotating configuration, we are utilizing this thing. Okay. Now, let me tell you, for these rotors, it may be possible that my rotor will be rotating at different speed. Yes. So, you can have two spool configuration in which one of the rotor will be rotating with the help of low pressure turbine, one spool that will be rotating with the high spool configuration, that means it will be rotated by high pressure turbine. We will be discussing the design for this in the session. So, we have a special week in which we will be discussing design of this contra-rotating configuration. That is what is most upcoming technology. Okay. Now, in overall, if we try to look at say what all we have discussed today, that is what is in sense of only rotor configuration, say inlet guide wave and my rotor configuration, my rotor and say outlet guide wave configuration or say stator configuration. We have inlet guide wave, rotor and outlet guide wave configuration. We are having contra-rotating configuration. Now, what all we learned today is, my whirl component, that is what is coming from my exit, that is what we are considering as one of the problem. Okay. And that is what. But based on your application where you are using this fan, that is what is very important. Okay. So, you are not bothering of having high pressure ratio or high pressure rise. There do not bother of this whirl component. If we go with the next configuration, what it say, we have tried to avoid our whirl component, that is what is coming out from my rotor exit. We found our exit to be axial one. So, basically we have not utilized the whirl component in sense what it need to be used for. We have we have nullified the effect of whirl component. If I am talking about this configuration in which rotor that will be followed by my stator, that is also having same kind of configuration. We have not done any implementation or use of whirl component. Okay. Now, even for the configuration of inlet guide wave, rotor and outlet guide wave configuration, we are not taking any benefit of whirl component, but we have realized the benefit of what whirl component, that is what will be coming out from my rotor 1, and that is what will be utilized in order to have my flow to be entering at my rotor 2, which is rotating in counterclockwise direction or in contra-rotating configuration. So, now being an engineer, we need to understand like how we will be using this kind of configuration. Suppose say you will be working for a company where people they are of no need to rise the pressure. Okay. Suppose you are making cooling fans for say your computer or maybe for your processors. Under that configuration, we are not bothering of our flow direction. We are only interested in cooling purpose where mass flow rate is of major concern. Then you need to go only with the rotor configuration. When we are looking for special requirement for axial exit, we will be having configurations like what all we have discussed. And this contra-rotating, that is what is giving you whole lot of benefits, like we will be discussing in detail when we will be going for the design of this contra-rotating fan. So, I am sure this is what is giving you new kind of feeling how we need to understand different kind of configuration for the design of axial flow fan or axial flow compressor. Let it be having application for say your commercial for industrial purpose, let it be having application for aero engine, let it be having application for say your land based power plant. So, here we are stopping with. Thank you very much for your attention.